Notice how the particles are arranged. If you had to guess, is this a solid, liquid, or gas? Solid, yes. So this is a solid. And what I'm going to do is I'm going to click this button where it says mark two atoms. And what it's going to do is going to shade in a different color for two of the atoms. And just like we studied before, how do the particles in a solid move? Yes, they're shaking in place. They are moving, but are they moving all around? No. Notice that the pattern they're in, they're locked into it. Notice these two atoms that we've marked. Have they changed locations? No, they haven't. Now, compare that with this one. Here's a liquid. I can tell it's a liquid right away. How can you tell it's a liquid? How can you tell it's a liquid, Anshul? It's not organized, okay? It's spread out a little bit more than a solid. I can also tell that it's not a gas. How can you tell it's not a gas? Gases aren't organized, but there's a sign here that's not a gas. Macy?
There's like more atoms.
Yeah, they're packed in too tight to be a gas. If this were a gas, it should be spread out more. Now, I'm going to still mark two atoms. Okay, do you see the two I've marked? And yes, they're in gray, and that's just to help us keep track of them. Now watch their motion as I press play. Remember we talked about how liquids flow? Notice how they're sliding past each other?
Where'd they go? There's there.
See, here's one right there. One's down here.
That one at the bottom really ain't.
Well, it's moving up now, see, as they bump into each other. All of these, I've made a link to these on the TCAP review site, so if you want to look at it at home, you can experiment with it a little bit more. And this website, Concord Consortium, they have tons of it, and I'm just using the ones that go with what we're doing now. So right away we can tell this is what? Yes, it's a gas. How can we tell it's a gas? How do we know it's a gas? Addison? Yes, it's really, the particles are really spread out. Now, I'm going to again mark two atoms. And then I'm going to press play to start the simulation. Notice how they're moving faster and they're bouncing off each other.
It's like
So we've talked about gases don't have their own volume. They continue to spread out. This is why. They're bumping into each other and they spread out more, bump again, spread out more. Now this time I'm going to pause it for a second. I'm going to pick an atom and I'm going to trace it. Let me unmark these two. Oh, it still marks them. Okay. I'm going to pick one to trace. And what it's going to do is going to trace the path that atom takes. So you'll get to see the line at where it's being. So you can kind of see how its motion is. So you can kind of follow it around.
Does it make different ones every time?
Yeah, so let me reset it. And I'm just going to put the trace on one of them. And I'm not highlighting any two. And so you can see how the motion, you'll start to see it. But you'll find it when you see. Do you see how they're bouncing off of each other? Now, we mentioned the other day that when we want something to change from a solid to a liquid to a gas, we have to either give it something or take something away. What was the something we said? Heat. Yes, if we've got a solid, and we're going to use water for our example because that's one we're very familiar with. If we have a solid and we want it to change to a liquid, we give it heat. If we want it to change to a gas after that, what do? Even more heat. What if we want to turn it back to a liquid?
We add like coldness to it.
I'm very glad you said it that way because a lot of people say it that way, and I want you to get this in your brain. Heat is a thing. It's energy. Cold is not a thing. We don't give cold something. Cold is a word we use to describe when there's less heat. Does that make sense? I'm glad you said that because everybody says that. I've said it. So, but yes, remove heat from it. If we want the liquid to go to a solid, then what do? We remove even more heat. Yes. So today what I want to do is talk to you about changing from solid, liquid to gas. On TCAP, they're not going to say, oh, is this a solid, liquid, or gas? They already know you know that. They expect you to know the words that we use, when something changes from a solid to a liquid to a gas. What is it called if you have a solid and you change it to a liquid? What's the word for that? Melting, yes. So, and what if you have a liquid and you change it to a solid? What's the word for that?
Evaporate.
No, liquid and turn it to a solid. Think of water. If you have liquid water, turn it to solid water, we freeze it. So today what I want to do is look at those words. Some of them you're familiar with, melting and freezing. Here's what I want to do first. I want to go to this demonstration. And we've got solid, liquid, and gas. Of course, could we have told that what each one was without that label?
Yeah.
Yes. Now, I want you to look at these 4 words. I think that 3 of them you're familiar with. You may not know exactly what they all mean, but one of them should be pretty new to you or not very familiar. We've got condensing, freezing, vaporization, and melting. Which one is kind of new to you? Or which one's kind of new to you? Macy?
Vaporization.
Vaporization. See, it's got that Z in it. Vaporization. Say it with me. Vaporization. Now, it should remind you of another word, though. What word does it remind you of? Maybe more than one. Will. Evaporation. It looks like evaporation, isn't it? And did you learn about water vapor last year?
Yeah.
When water's a gas form? Yes, you may have heard in science fiction movies that they're going to vaporize somebody. You know, it means they're going to turn them to a gas. So vaporization is the word. Stay with me. Vaporization is the general word we use to turn a liquid to a gas. Now, you can do it really fast, and it happens at a certain temperature, or it can happen slow. You learned about the slow one in the water cycle. What's the word when you have a liquid in the water cycle and it turns to gas and gets in the air, Addison? Evaporation. The other one you've heard your whole life. When your parents are cooking, you've heard this. If you have a liquid and you turn it to a gas really fast and it happens at an exact certain temperature, what's that called? Laura? Boiling. So boiling and evaporation are both forms of vaporization. Turn a liquid to a gas. Boiling's the fast one. Evaporation's the slow one. We'll talk more about it in just a second. So far, so good? Now, but we need to match these up. Solid to a liquid. Which one of these is solid to a liquid? Think of water. If you have a solid water, turn it to a liquid. Which word is it? Ethan? Melting. And on this, if it's wrong, it'll bounce it back. Yes, we're right. And then liquid to a gas, just the general word, liquid to a gas, Isaac? Yes, and vapor means gas. So to vaporize something means to turn it to a gas. So it makes me feel very Doctor Who-ish when I say something like that, you know. I'm going to vaporize you. Now, here's the next thing I want to look at. Here we have a beaker, and it's got ice in. I know it's hard to see with our projector. And underneath we've got a Bunsen burner, which basically just puts a little gas flame underneath it. Right now it's at negative 15 degrees Celsius. Do you remember the temperature from last year that water will go from a liquid to a solid? Do you remember, Braden? Yeah, that's the Fahrenheit. Remember, that's such a random number. And then in the Celsius scale, it's much easier to remember. What's the number? 0. Yes, metrics is so much easier. 0 is way easier to remember than 32. That's random. So to me. So right now it's below 0. Notice the C there lets us know it's not Fahrenheit, it's Celsius. Yes. So this is it's 15 degrees below 0, and then the ice is still solid. When I hit the heat button, what do you think is going to happen here? It's going to melt. How will we know it's melting? What will be the signs? What will we see in the container as it melts? Eli?
It will turn into water.
Yeah, it's going to go back to the liquid. It's water now. It's the frozen water, which is ice. It'll go back to liquid water. Yeah, so we need to avoid trying to use the everyday words that we use, at the house or just with our friends, because in science, it has a very specific meaning. Ice is not always water. You can take a liquid, you can take methane and make it an ice, the solid version. At what temperature will we see it start to change over?
0.
When it hits 0. So the melting point for water is at 0. Will it immediately turn everything, all of it melt immediately? No. What's going to happen, part of it's going to melt first. Which part should melt first? The bottom. Why would the bottom melt first? Why would the bottom melt first? Addison. Yes, it's closest to the source of heat. Now, one of the weird things about this is this idea that if you had a thermometer in here, when it hits zero, the thermometer, it's going to start melting. And even though the heat is still on, the overall temperature of the water is not going to increase yet. But once all the water is turned back to liquid, then the heat can be used to raise the temperature of the water, because what's happening is that even though the heat's still on the whole time, the ice that's still left over is kind of keeping everything cool. But once all of it gets melted, then it's going to heat up. Let's watch. Temperature's rising. It's at zero. Notice it's still at zero, even though the heat's still on. Now it's still at zero. It's all melted. We keep the heat on. Now the temperature is going to increase. Now I'm going to hit the heat again. What will eventually happen when I continue to add heat to it? Marissa? Well, remember, evaporate's the really slow one. Is this going to happen over a course of hours? Yes, it'll boil, and the specific one, it's going to boil. Yes, it's going to hit that temperature that water needs to get to change to a gas. Now, does anybody remember that temperature? What is the temperature that water has to get to turn to a gas? Avery? 212 degrees Fahrenheit. Can you get more random than that? I think not. But in the Celsius scale, much easier number to remember. What temperature is it? 100. Yes, so much easier. So when it gets to 100, we'll see it start to change to a gas. What will be the signs? What should we see in the liquid that lets us know, oh, it's changing to a gas? What's one sign we'll see, Anshul? You will see bubbles. Yes, these particles, as they get enough energy to turn to a gas, they'll be trapped in here. Anytime you see a bubble, that's a gas that's trapped in a liquid. Have you ever blown bubbles when you were little? What you're doing is you're taking a soap and water solution, a liquid, and you're trapping a gas, the air, inside it. That's all bubbles are, gases trapped in liquid. Your soda, Coca-Cola, you've seen bubbles in it, right? Carbon dioxide gas trapped in the liquid. And since gas is less dense, it floats to the top. Remember, the less dense material floats to the top. So we'll see bubbles. What else might we see that lets us know it's changing to gas? Cole? Yes, we're going to start seeing some steam come out. Now, we'll see it at first, but eventually it'll spread out. We won't see it as much. Anything else we might notice? What's another sign, Ian?
There won't be much water.
Yes, so as the liquid molecules change to gas, there are going to be less liquid molecules, so the water level will go down and go down. Have you ever seen that happen at the house? Your parents have something on the stove and they have water in it, and then they come back and they have to add more water? You ever seen? Yes, because as that water in the food or the beans or whatever it is you're boiling, it turns to gas. It gets in the air, and then I have like some kind of lids. You may have these at home. They have like a little pressure release thing, and it like bobs up and down and it pushes on it so that the gas can escape. Because if you don't, the force of the gas, it spreads out so much, it'll actually push the lid off. So yes, we'll see lowered liquid level. We'll see bubbles. We will see some steam at first, but as it spreads out. Now, notice something here. Is this container open? No. So the water that changes to a gas, is it going to be able to get out into the room? No, it's going to stay in the container. So let's click heat. And we said around what temperature will it change over? 100. This is Celsius, so we won't see the 212. So Bunsen burner's on. Starting to heat up. Now, I wanted you to know something. Now, see the water level went down. And you can see it. Well, it's hard to see because it's projector. It's not as clear. But I want to point out something to you. Before it got to the whole thing had 100 degrees, there were some bubbles already. Because the particles that were closest to the flame, those particles got to 100 before the whole water was to 100. Now, if we keep on applying heat, what's going to happen to all this water? Well, maybe not explode if there's enough room in the container. There's probably enough room in the container, so it won't put that much pressure on it. But eventually all the water will change over to gas. It'll all be trapped in there. If we cool it off, what's going to happen? turn to your neighbor. If we cool it off, what will that water in the gas form do? Okay, so tell me, if we remove heat, let this thing cool off, what will we see happening? What will we see happening, Jacob?
We'll have liquid water there.
Mm-hmm. Well, there's water in it the whole time. It's just in a gas form. Laura?
If you put it at room temperature, it will go back to water.
It's all water. It'll go back to
It'll go back to
liquid. It'll go back to the liquid form of water because it's still water, even though it's a gas. Okay. So have you ever seen that happen before? The drops of water collect on the inside of the container, because what's happening is that water evaporates into the air. But if the container is sealed, once the temperature drops, then it'll collect on that. You'll see little drops of water on the inside of it. I don't know if you've ever seen a terrarium. It looks like an aquarium, but it has plants in it. You'll see that little drops of water collecting there.